Okay. Okay, it's time to can you hear me?
Yes.
Okay, I think it's time to start the talk. Yeah, welcome everyone, and we are very happy to have Professor Bruce Allen from Albert Einstein Institute to give us a talk about this topic. And may I have some very brief introduction to the speaker today? And Professor Bruce Allen and got his PhD, bachelor degree from MIT back in 1980, and supervised by Werner Wyss. We know Werner Wyss, yeah, just the LIGO founder, and got a Nobel Prize. Not just about 10 years ago, less than 10 years ago. And then Booth went to Cambridge, England, to study graduate school under Hawking, Stephen Hawking. So, and everyone knows Stephen Hawking. I don't need to say more about that. And I have a long list of his academic appointments and awards, honors. I just highlight some. And after the obtaining the PhD, he settled down in University of Wisconsin, Milwaukee, for quite a long time, and then moved to Albert Einstein, went over as a director. And we know I know Bruce a long time ago, almost 3 decades ago. I met the first time in a slow mass. I as a member, and I know Bruce not personally, but his work very well. Yeah, I read a lot of his famous paper, and he's an expert in cosmic microwave background. This is the main topic today, and a lot. I just mentioned a few about cosmic strings, also numerical simulation, and so many. And I don't have time to mention. If you're interested, just type Booz Allen and Albert Einstein Institute. I could find. I bet you could find more information about his profile. Okay, I don't want to waste a lot of time. And before we start, I would say I would just mention some rules during his talk. And Bruce, he really want to be more interactive, interactive in his talk. So if you have questions anytime, please raise your hand. I will unmute you, and you can ask directly questions to Bruce, or you don't want to speak, and you can type on the chat bar, and I will repeat your questions to Bruce. And I think let's, as Bruce instruct us to do, he wants to be more interactive. So please just enjoy his talk. Okay, Bruce, go ahead.
Well, thank you very much for the kind introduction. As Ken said, I don't like going to talks on Zoom, and I don't like giving talks on Zoom because I can't interact very easily. So if I've said something that you're curious about, or that you don't understand, or you want to ask me something, please interrupt. I've planned a talk which is going to take an hour, and we have 1.5 hours. So if you interrupt me to ask things, that's absolutely fine. You can put up your hand, and Ken will call on you, or you can type something in the chat and he'll repeat. So please do that. So I'm going to talk today about gravitational wave stochastic backgrounds and pulsar timing arrays. Gravitational wave stochastic backgrounds are a topic I've come back to and worked on for more than 40 years because they offer us the potential to see what happened in the very early universe. And there's no other good way to do that. My interest in this topic began almost 50 years ago through my contact with Ray Weiss. Ray was my first physics professor at MIT. I met him when I was 17 on the 14th of September, 1976. And Ray hired me the day that he met me to work in his lab. He's had an enormous influence on my career. He's known as one of the founders of LIGO, for which he won the Nobel Prize. But at the time that I met him, he was actually working on microwave background radiation experiments. And I wrote an obituary for Ray, which was published in Nature a few weeks ago. So if you'd like to know a little bit more about Ray, have a look there. And the photos here on the left show Ray as he was when I met him almost 50 years ago. And then here on the bottom right, this is a picture from about 25 years ago. Along with Stephen Hawking, Ray was one of my two constant advisors through my career. Also, just to set the scale of 50 years ago, this is a photograph taken of me in Ray's lab in 1976. I'm actually working here on a microwave horn, which is a receiver for the electromagnetic background radiation. And if you look carefully at the clock here, you can see that it's the small hours of the morning. So I want to begin with an introduction to this topic. We all know about the electromagnetic background radiation. This was discovered by Penzias and Wilson in 1964, 1965, using this horn antenna that was operated by Bell Laboratories. What they discovered was a faint background of 2.7 Kelvin blackbody radiation. It was isotropic, left behind from an early phase of the universe. This gives us a picture of the universe when it was about 300,000 years old. Because at that point, the charged particles, electrons and protons, recombined, and the universe became transparent. So the radiation, about 4,000 Kelvin at that time, has been redshifted by the expansion of the universe and is now 2.7 Kelvin. Ray Weiss actually worked on the COBE satellite, which made the first good measurements of the spectrum of that radiation, and also measured the first few multipole moments of it. Now, if you subtract the 2.7 constant uniform background, and you also remove a dipole term coming from the motion of our local system, what you're left with are pictures of the universe. These are Planck satellite sky maps at different frequencies. And the fluctuations that you see, these perturbations, have a huge amount of information about cosmological structure at that time and at subsequent times. So the goal is to do, there's a question, please go ahead.
Actually, I don't see slides, so you should share the slides first.
I thought I am sharing. It says I'm screen sharing.
Yeah, I can see it very well. Yeah, I don't understand why on your side you can see it. Yeah.
Should I go ahead or should I try stopping my sharing and restarting it?
And who else cannot see it? Yeah, it seems, yeah, I think most of them can see it. Yeah, I think it's maybe some problem on your own side. I think Bruce, you can go ahead and let the gentleman figure out how could you see the slide.
I do that.
Hmm.
So the gravitational wave background, the idea is analogous. We want to look for radiation, but gravitational waves in this case. Now, gravitational waves, I'm not going to say much about them, but again, as part of the introduction, just briefly, Gravitational waves were predicted by Einstein in 1916, less than a year after he published the general theory of relativity. And the paper about it is shown here on the left. It has a very technical title. It says Perturbative Solutions of the Field Equations of Gravitation. And in this, he shows that if you have masses which are accelerating, then what happens is they emit waves. They cause perturbations of space-time which propagate away at the speed of light. And we'd say today that this is a massless field with spin 2. Gravitational waves were observed indirectly in 1975 by Russell Hulse and Joe Taylor. They observed a system of two neutron stars orbiting each other, PSR 1913 plus 16. This system orbited about once every 8 hours. And what they observed was that with each orbit, the radius of the orbit got smaller by about 3 millimeters. And that's because the system was losing gravitational binding energy and emitting gravitational waves exactly as predicted by Einstein's theory. The first direct observation of gravitational waves by the Laser Interferometer Gravitational Observatory was almost exactly 10 years ago in 2015. It's illustrated here on the cover of Physical Review Letters, where you see a black hole of 30 and 35 solar masses orbiting each other and merging over a space of about a quarter of a second. And you see here the waveforms from the two LIGO instruments. And then this is meant to be a schematic representation of the 62 solar mass black hole that resulted from that. So gravitational waves cover a very broad range of frequencies, just like electromagnetic radiation. At the high frequency end, with periods of milliseconds and frequencies of 100 or 1,000 hertz, is radiation produced, for example, by the orbit and merger of stellar mass objects. These could be black holes or neutron stars. And these are the types of signals that are now picked up by ground-based detectors like LIGO. At lower frequencies with periods of hours are signals produced by more massive black holes or by small mass objects falling into extremely high mass objects or orbiting them. And these types of signals should be visible in space-based detectors like LISA, which is scheduled to launch in 2034. At the longest wavelengths, meaning frequencies corresponding to, for example, 100 cycles in the age of the universe, gravitational waves should appear as correlations between the polarization and temperature perturbation patterns in the electromagnetic background radiation. But the topic today, I want to talk in the later part of my talk about pulsar timing arrays, or PTAs. These are detectors of gravitational waves with frequencies in the nano-Hz regime. So 1 nanohertz corresponds to 1 gravitational wave cycle in 32 years. And what you have down here is a schematic image of a radio pulsar timing array, and I'm going to talk in some detail about how those work. So I want to say some general things about gravitational wave stochastic backgrounds. And to begin that, there's the motivation here. So gravitational waves are the perfect early universe messenger. They carry information about it because they couple so weakly. So, for example, if we look at the universe in electromagnetic radiation, we can look back to 300,000 years after the Big Bang. But at that point, earlier times, the universe contains a lot of charged particles. Those scatter photons. And so we can't see through that optically thick medium anymore. But the weakness of the gravitational wave coupling means that we can see much earlier times. In fact, gravitational waves couple so weakly that they probably never had any opportunity to come into thermal equilibrium. So whatever gravitational waves are left behind from the early universe are most likely non-thermal. And I'll show some examples of that. Now, to talk about the gravitational wave background, it's very useful to introduce a spectral function. This is to describe how the energy is distributed as a function of frequency. And it's conventional in this topic to use a dimensionless function called omega of f. So f here is gravitational wave frequency. On this plot, I've gone from 10 to the minus 18 hertz to 10 to the 15 hertz. So this is a range of frequencies from one cycle in the age of the universe up to the frequency of visible light. So this is a very broad range in frequency. And the definition of omega is the following. You look in a range of frequencies between f and f plus df, and you let d rho, gravitational wave, be the energy density in that frequency range. You divide d rho by df, so that's the energy density per unit frequency, and then you normalize it to make it dimensionless. You normalize it with the factor of f in the numerator, and in the denominator you put the critical energy density that's required to just close the universe today. So this dimensionless quantity, I've illustrated it in this plot. If the gravitational wave stochastic background was just like the electromagnetic spectrum, that is, it was a 2.7K black body. Now that's not likely to be the case, but it's a nice way to illustrate what this plot means. So for example, the peak here is at about 100 gigahertz. That's in the infrared. And you'll notice that the magnitude here at the peak is about 10 to the minus 5. I guess I didn't label this as a log base 10 scale. The reason for that is that the electromagnetic background radiation is about 1/100,000th of the closure density of the universe. So just from the fact that we have a peak here whose width is, let's say, of order 1 in log space and has a magnitude of 10 to the minus 5, you can see what fraction of the energy density of the universe is in this radiation. And I've drawn a horizontal red line here around 100 hertz. That's the current limits on the stochastic background from the LIGO experiment. You'll see later that PTA limits down at frequencies of around 10 to the minus 9 hertz are at a comparable level. So I'm going to use this function omega of f to talk about some different gravitational wave sources. And so please keep this definition in mind. I want to give a few examples of gravitational wave backgrounds and how they're produced. The first example was the thing that really got me working on this topic. This was back in the 1980s, and actually Ray Weiss was the motivation for this. I was a postdoc in Santa Barbara. Ray ran into me and he said, "Bruce, I know you're working on inflationary models. Listen, could you calculate what the gravitational wave stochastic background from inflation is? Because that might be a useful target for LIGO, but we don't know how big that would be." And the mechanism that produces this background is well known. I tend to think of it in the following way. During inflation, matter fluctuations pass outside the Hubble sphere of any observer very quickly, and what you're left with is a cosmological constant dominated universe with just vacuum fluctuations. And so here's a mass on a string, that's a harmonic oscillator. You have to imagine that that's in its ground state. So there's 1/2 h bar omega of energy here. But what happens is the expansion of the universe is so rapid that this frequency is redshift. And so here I've rolled out the string to lower the frequency of the harmonic oscillator. Now there's two cases. If you roll out the string slowly, adiabatically, then this mass stays in the ground state. But if you do it quickly, then what happens is the 1/2 h bar omega of energy from this initial state is still there, but the frequency is much lower. And so you end up with a large occupation number. You end up with a coherent state. And this is what happens in inflation. The universe expands so quickly that your 0-point fluctuations turn into large occupation numbers. This is also called parametric amplification or particle creation in an expanding universe. And this is a universal clean signal of inflation. And it leads to a spectrum like the following. Now, let me warn you, this is not in the units that I just talked about. This is actually just a snapshot. I believe this is the first calculation of this spectrum in the literature in 1988. And, and what you see here in the vertical axis is energy density. So this is ergs per cubic centimeter per hertz. And so there's a low frequency part here. These are perturbations that re-entered the universe, re-entered the Hubble sphere before the universe became matter dominated. Then there's the ones that re-entered after. That's this part of the spectrum. And over here on the right, I've just sketched these thermal spectra that I talked about before, just to give you something to compare to. So if I normalize this energy density in the way that we just discussed a minute ago, here's the result. So this is an inflationary gravitational wave background produced by slow roll inflation. It has this steep section here at low frequencies, and then it has a long flat part, and finally falls off at a frequency determined by the speed of the phase transition at the end of inflation. Now, what's a bit unfortunate about this is the magnitude. In typical slow roll inflationary models, the maximum amplitude that you can get over frequencies, for example, around 100 hertz where LIGO is sensitive, or 10 to the minus 9 hertz where pulsar timing arrays are sensitive, is about 10 to the minus 15. So this is a very clean and interesting signal, but unfortunately not a very strong one. Here's another example of a gravitational wave mechanism to produce gravitational waves in the early universe. Here the idea is that you have a phase transition early in the history of the universe where a local U1 symmetry is spontaneously broken. And what happens is you form one-dimensional string-like objects called cosmic strings. And in the bottom right here is a simulation showing what happens after the string network is formed and the universe expands. And what you're looking at here is a single Hubble length. And what happens is these strings move relativistically, and they chop off little loops. Those are shown in red here. And those loops then oscillate and emit gravitational waves. And this process continues indefinitely. You reach a scaling solution here. And this process produces a broad spectrum of radiation. And here's a here's a snapshot of what that radiation would look like. So again, I'm plotting this dimensionless spectral function omega as a function of frequency. Now, I took this from a 1992 paper where the best limits on the mass per unit length of the string were about 10 to the minus 6. So if you look here at the spectrum, what you see is two parts. There's a low frequency part here, and this is produced by loops of string that started radiating after the universe became matter dominated. And then there's a higher frequency part here produced by loops that formed at earlier times before the universe became matter dominated. And you can see that that there's a characteristic peak here and then a falling spectrum. At the time that we did this work, a model like this would have been acceptable, but the limits on gravitational wave amplitude at these nano-Hz frequencies here are so much better now that in fact this model is completely ruled out, and you'd have to decrease the mass per unit length of the string by many orders of magnitude for this model to be observationally acceptable. So that's a second example. The last example I'm going to give is a little bit different than the others. And this is because the gravitational waves in the previous two cases were produced by early universe processes. But here, the gravitational waves in this example are simply produced by unresolved binary systems radiating gravitational waves in the same way as that chirp that you saw in the LIGO signal. So here, the idea is that we can detect nearby mergers, but there is a background of other mergers that are more distant, which aren't individually resolvable. And so these add together to produce a weak stochastic background. And that stochastic background is illustrated here in this blue curve. That's a total. In the green curve, that's binary black hole contributions. And in the red curve, that's the binary neutron star contributions. So here the range of frequencies corresponds to terrestrial detectors like LIGO and Virgo. And you can see that when advanced LIGO reaches its design sensitivity, that's this dotted curve, it will become sensitive to this unresolved signal from inspiraling and merging distant systems. Now, as I explained earlier, my real interest here is actually in seeing processes that took place early in the history of the universe. So in some ways, this background is more a hindrance or a problem. Now, it carries lots of interesting information about the population of black holes and neutron stars, but in some ways, this should be thought of also as a foreground that gets in the way of seeing a gravitational wave background of cosmological origin. All right, and I want to just finish this general discussion by showing you here a kind of landscape of where things currently stand. So again, on the horizontal axis, I have a very broad range of frequency from 1 cycle in the age of the universe up to gigahertz frequencies. This bottom blue curve here, this is the prediction from slow roll inflation. There's an old paper by Mike Turner showing that in slow roll models, this particular tensor to scalar ratio is the thing that maximizes the amplitude at, for example, LIGO or LISA or PTA frequencies. And so this is actually an upper limit. You can't do better than that in slow roll inflation. Up here are some curves showing the current limits from advanced LIGO and the potential design sensitivity limit here. This square box here is the part that I had cut out to show you this background from binary black holes and binary neutron stars, these two curves. This is the sort of limit that, that LISA ought to achieve in its observations. And finally, over here on the left are the current PTA limits on a gravitational wave background. You'll notice that the sensitivity here is at about the 10 to the minus 9 level. Some of the other curves, these indirect limits, for example, come about from Big Bang nucleosynthesis, observations of the Earth's normal modes. Okay. And lastly, I'd like to say just a little bit about the epoch in which gravitational waves might have been produced. Now, the idea is this. Suppose that we detect gravitational waves of cosmological origin. As you've seen from the inflationary example and from cosmic strings, this radiation is produced when there are processes taking place at the Hubble scale. So, for example, in inflation, it's when perturbations re-enter the Hubble sphere after inflation has finished. Or in the case of cosmic strings, it's when you cut off loops whose size is comparable to the Hubble radius. So here's the picture. What I've shown on the horizontal axis is cosmological time as seen by a co-moving observer. So you imagine an observer, they're just looking at their wristwatch as the universe evolves. They're freely falling, floating in space. And here's the Hubble length. This is 2 times t, or I'm sorry, it's just c times t, I should say. It's the distance to the Hubble horizon, and that's growing linearly as a function of time. So that's the cosmological length scale. Now, this lower curve is the physical wavelength of a gravitational wave, and you should imagine that this time today here, 10 to the 17 seconds after the Big Bang, is when we've observed it. So we observe it today with some wavelength. So let's trace that gravitational wave backwards in time. as it blue shifts going to the past. So the wavelength gets shorter, first like t to the 2/3 when the universe is matter dominated, then like t to the 1/2 when the universe is radiation dominated. You'll notice that these two curves cross at some point in the past. And that's the time when those waves would have corresponded to a Hubble length, the wavelength of the waves. So if the gravitational wave detector sees waves that are of cosmological origin, then they were produced at the time when these two curves cross. So for example, for LIGO, which is sensitive to frequencies around 100 Hertz, those are wavelengths of 3 times 10 to the 8 centimeters. If we track that back in time and we ask where that crosses the Hubble length, it's about 10 to the minus 22 seconds after the Big Bang. That's fantastically early time. What about LISA? LISA is sensitive to wavelengths that are 4 orders of magnitude longer, frequencies 4 orders of magnitude smaller. And so you move these curves up, and you can see, for example, that LISA would be sensitive to cosmological processes at times about 10 to the minus 14 seconds after the Big Bang. So roughly the electroweak phase transition energy. Pulsar timing arrays are sensitive to much longer wavelengths. And so those, if we see processes of cosmological origin, that would be processes occurring about 1 second after the Big Bang. Okay. So that was my introduction to gravitational wave stochastic backgrounds and just some general principles. And now I want to shift gears and spend the last part of my talk talking about pulsar timing arrays. These are detectors for nano-Hz gravitational waves. I want to talk about how pulsar timing arrays work. I want to talk about what the current status is and a little bit about what I anticipate for the future. This might be a good point. There hasn't been any questions, so let me just stop here briefly and just ask if there's any questions somebody would like to ask.
I don't see any hand for the moment. So.
Okay. All right, I'll carry on. Okay. So pulsar timing arrays are sometimes called galactic-scale gravitational wave detectors. In a gravitational wave detector like LIGO, you have arms that are a few kilometers long, 4 kilometers long, and you're detecting waves that have wavelengths of thousands of kilometers. So the detectors are much smaller than the gravitational wavelength. Here instead, we observe signals from many different pulsars at the Earth. And as the gravitational waves travel by this system, they induce changes in the clock signals that we see from these pulsars. So I've seen this picture many times, and I just want to give you a warning that it's not to scale in many ways. Clearly, the Earth here is way too large. That's one sense in which it's not to scale. But there's another important thing here which is wrong, which is if you look at the wave here, the wavelength of this green background, it looks like it's comparable to the distance between the Earth and the pulsar. But that's really not right. It takes light from the pulsars thousands of years to reach Earth, whereas the wavelength of gravitational waves that these detectors are sensitive to are wavelengths of order 10 years. So really you should see hundreds of cycles of the wave along each of these yellow paths. Now the period of the clock here, so these pulsars are just acting as a frequency reference or clocks. And their period is about a millisecond or a few milliseconds. That's about 10 to the minus 10 years. So what you have to imagine is there's a train of pulses, approximately 10 to 13 of them, passing along this yellow path. And finally, I haven't shown you here the distance to the gravitational wave sources. If this picture here is about 1 meter in size on your screen, then those sources are 100 kilometers away. So they're effectively distant point sources and not visible in this diagram at all. So in a pulsar timing array, the pulsars act as precision clocks. In the analysis, any effects that cause these pulsars to deviate from perfect clocks, for example, a motion in a binary system, get removed. And so if there's no gravitational wave background, then what happens is the pulses arrive completely uniformly. But if there's a gravitational wave background, that perturbs the arrival time of the pulses. And I just wanted to show you the calculation, how you can compute what the effect of the gravitational waves is. It's the same effect, the Sachs-Wolf effect, that causes perturbations in the temperature of the microwave background radiation. This was worked out by Sachs and Wolf in the 1960s. And if you work in a transverse traceless synchronous gauge, here's how it works. So I've got a space-time diagram here showing the Earth at rest at x equals 0 and a pulsar at distance L from the Earth in direction p hat. And I've drawn here the null path followed by a pulse of radiation as it leaves the pulsar and travels a few thousand years to reach Earth. And Sachs and Wolf computed the time delay caused by a gravitational wave along that path. And the way that you get it is you take the components of the metric perturbation in the direction to the pulsar, and you integrate that metric perturbation along this null path. So as the parameter s goes from 0 to L, we move along the path from the pulsar to Earth, and we sample the metric perturbation along this null path. So the arguments here, t minus L plus s and L minus sp hat, are just tracing out a point on this dotted curve or dotted line. Now, if you want to know the fractional change in frequency of the clock, that's the redshift, you have to take the derivative of this timing residual with respect to t. Now, if you do that, you'll notice that you're differentiating an integral. And so when we do that, we're left with two terms, one at each boundary, at the upper and lower ends. And so this formula only contains two terms. It tells you that the redshift, the fractional change in the pulsar's rotation frequency as seen from Earth, is just obtained by dotting the direction to the pulsar into the components of the metric perturbation. Down here is a factor that's 1 plus the dot product of the gravitational wave propagation direction with the pulsar direction. And then there's the difference between the two boundary terms. Now the lower term here is called the Earth term because it's the gravitational wave amplitude evaluated at time t at the location of the Earth. The other term is the gravitational wave amplitude evaluated at the time that the pulse left the pulsar at the location of the pulsar. So this difference is what's seen in pulsar timing arrays. Now, if the gravitational wave amplitude were large enough, if this h were big enough, we wouldn't actually need an entire array of pulsars. We could actually see these terms in the arrival times of a single pulsar. And in fact, in the early work in the 1980s and 1990s, people set upper limits on gravitational wave backgrounds just by looking at single pulsars. But we now know that h is too small. And so the way that pulsar timing arrays work is they exploit the fact that this term here, the gravitational wave at the Earth at time t, that's the same for all pulsars, apart from this geometrical factor in the front, which I'm going to come back to in a minute. These other terms here, these are the gravitational wave amplitudes evaluated at points in space that are thousands of years apart at different times. And so the idea is that these pulsar terms here are not correlated with each other, but the Earth terms are the same for all pulsars. And so exploiting that fact is how pulsar timing arrays. They look for this common effect in many pulsars. So just again to emphasize how these work, here's another nice analogy. You can imagine that the train of pulses coming from a pulsar is like cars going down a track. The spacing between these cars is set by the rotation of the pulsar. So each pulse, let's say, is in between a pair of cars. When these pulses leave the pulsar, the ruler, which is determining the spacing here, is modified by the metric perturbation at the time the pulse was emitted at the location of the pulsar. So that sets the spacing. And then these cars start traveling down the 1,000-year-long track until they reach the Earth. And so this track has 10 to the 13 cars along it. But when the cars arrive at the Earth, we measure the spacing again. And when we measure the spacing at the Earth, the metric perturbation at the Earth also modifies the measurement. So that's another way of thinking about how PTAs work. Now, the long-term goal of pulsar timing arrays is to make maps like this. This is what we would like to do, but it's still quite far in the future. So ideally, for example, maybe 50 or 100 years from now, we'll have maps of the gravitational wave sky in the nano-Hz frequency range. And for example, we'll be able to identify certain discrete sources. We'll say, for example, that there's a source that consists of two supermassive black holes orbiting each other. We'll know what the masses of the black holes are. We'll know what the inclination of the orbital plane is. We'll be able to say that it has a 76-year orbital period and what the distance is. And so we'll be able to identify some discrete sources on the sky like that. And then there will also be some sort of a diffuse background. And hopefully we'll be able to measure and characterize that the same way that we do with the microwave background radiation. And what the origins of that might be, I think we can only speculate on today. So that's the long-term goal. Now, pulsar timing arrays are not there yet. And I want to explain where they are at the moment. So in understanding how pulsar timing arrays work, there's a very important curve which appears called the Hellings and Downs curve. This was first computed by Ron Hellings and George Downs in 1983. And the curve can be thought of as a mean correlation, and it's a function of the angle between the line of sight to two pulsars. So the idea is you look at one pulsar in the sky, you look at a different pulsar at a different location in the sky, and there's some angle gamma between those two different lines of sight. So gamma here is the horizontal axis. And what I'm showing here on the vertical axis is the mean correlation between the arrival times or the timing residuals in the two different pulsars due to gravitational waves. So as I said, this correlation arises because the Earth term is the same for all pulsars. And if you have two pulsars that are in exactly the same direction on the sky, but somewhat different distances from the Earth, then the Earth term of those two pulsars is correlated, and the pulsar term is uncorrelated. So that means that the correlation is exactly a half. That's this point. If you now move those two pulsars apart until they're separated by, say, 90 degrees on the sky, then on the average, they're actually anti-correlated. And this pattern here of correlation and anti-correlation between different pulsars, this is the smoking gun that you've seen gravitational waves. It's the pulsar timing array equivalent of this chirp signal seen by LIGO. And I just wanted to show briefly where this curve comes from. As you recall, a minute ago, when I was showing you how the Sachs-Wolf effect leads to correlations, or leads to redshifts in pulse arrival times, there was this antenna pattern function here that occurred. So this is the dot product of the direction to the pulsar with the component, the polarization tensor of a gravitational wave traveling in direction omega. So this is the response of a pulsar to a unit amplitude plus polarized gravitational wave. And if you have two different pulsars, so two different vectors, P1 and P2, then the average correlation between the Earth terms for an unpolarized source is just obtained by taking the products of these for the plus polarization, for the cross polarization, and adding them together. And what Hellings and Downs did in 1983 is they asked, if you have an unpolarized isotropic background, how does this correlation work if you average it over all the possible sources? And so what they did is they integrated this correlation over all gravitational wave directions to compute a mean correlation. And that's this curve mu here. So it actually has a nice closed form in terms of the angle gamma. And searching for this curve and seeing it, that's currently what pulsar timing arrays are trying to do. Now this curve is just the raw monopole moment. So this is a bit like trying to see the 2.7 Kelvin background. Nothing to do with the perturbations yet. In fact, this curve is so important that the International Pulsar Timing Array Detection Committee published a checklist. And in their checklist, they said that to demonstrate that gravitational waves are creating some of the noise in pulsar timing datasets, observations must exhibit the Hellings and Downs curve, the angular correlation function associated with gravitational waves, as well as demonstrating that there are no other reasonable explanations. So here's the current status right now of PTA observations. In June 2023, 4 PTAs published on the same day their current results. The Parkes Pulsar Timing Array, PPTA, observed 24 pulsars over 18 years, and they concluded there was no support for or against gravitational waves. The European Pulsar Timing Array observed 42 pulsars for 25 years. Now, if they analyzed that full 25-year data set, they reported marginal evidence for gravitational waves. If they took only the last 10 years of that, they report evidence. Now, that's a little bit strange because the 25-year data set should be more sensitive. These are low-frequency signals, and the longer observation time gives you more sensitivity. The Chinese Pulsar Timing Array, CPTA, used the FAST telescope to observe 57 pulsars over 3 years. They reported some evidence. The North American nano-Hz Observatory for Gravitational Waves, NanoGrav, observed 67 pulsars for 15 years. They reported what they called compelling evidence. Now this means something between 3.6 and 4.2 sigma. So that doesn't meet the 5 sigma detection threshold, which is standard in particle physics and in gravitational wave physics. The most recent results this year are from MIRTIME. MIRTIME used the MeerKAT radio telescope to observe 83 pulsars over 4.5 years. And they reported something interesting. They said that under different assumptions about the noise processes, we can produce either what appeared to be compelling Hellings and Downs correlations of high significance, 3 to 3.4 sigma, with a spectrum close to that which is predicted from a background produced by supermassive black hole binaries, or surprisingly, under slightly different assumptions, correlations that are insignificant. So I think it's fair to say that there is evidence for gravitational waves at these nanohertz frequencies, but there's not yet a detection. Here's what the different PTAs report in their reconstructions of the Hellings and Downs curve. So this line here, for example, represents the curve that we just talked about, the pattern of correlations between different pulsars. And here's the PPTA reconstruction. Here's the NanoGrav reconstruction, the MIRTIME one, and so on. So a research question that I've worked on quite a bit during the past several years is the question, how close do we expect this reconstruction to actually come to the curve? That's very relevant for the detection problem, and I'm going to talk a little bit about that now. So let's look carefully at the nanograv reconstruction of this Hellings and Downs curve. So again, we have on the horizontal axis the angle in degrees between the line of sight to different pulsars, and the vertical axis a mean correlation. And this dotted curve shows this expectation for an isotropic and unpolarized background. So nanograv observed 67 pulsars. That means that there are 67 times 66 divided by 2 different possible pairs of pulsars. So that's n times n minus 1 over 2. 2,211 possible pairs of pulsars. So what they've done is they've taken those 2,211 different pairs and they've broken them into 15 bins. So there's about 147 pairs in each of these 15 different angular bins. So this point here, this blue point, represents the average correlation of 147 different pulsar pairs with angular separations between 0 degrees and going up to about, say, 20 degrees. This next point represents the average correlation of the next 147 pairs of pulsars with larger angular separation. So the blue point here represents the mean correlation of those pairs. And these uncertainty bars they don't represent the range of the correlation, they represent the uncertainty in estimating this mean. And you can see that many of these uncertainty bars intersect with the Hellings and Downs curve. So that looks encouraging. But we'd like to know what range of uncertainties here do we expect? And that's a topic I've worked on quite a bit during the past several years. So there's a history to this, and the history goes back to 2017 to a somewhat unrecognized paper by Rober and Holder. They asked the following question. They said, suppose that you have an infinite number of pulsars, so they're uniform on the sky, that there's no sources of noise. So these pulsars are measuring only timing residuals or timing delays due to gravitational waves. Then they said, let's suppose that we have a Gaussian ensemble of unpolarized sources, and all of these sources are radiating at the same frequency, 1 over t, commensurate with the observation time. So by making all of these simplifying assumptions, they were able to use techniques from cosmic microwave background sky mapping to compute what the variance would be. This is cosmic variance. The idea is that any given instance of the universe has sources with different gravitational wave phases. Those produce interference patterns on the sky. And so for any given universe, even after you average over all of these pulsars, you don't get exactly the Hellings and Downs. You get something close to it. And they computed that variance. So in the past year, my collaborator Joe Romano and I, got a picture of Joe here, have worked out now what the optimal way is to reconstruct this Hellings and Downs correlation, and we've computed what the variance should be. So how far should the observations fall away from the curve? And what we've done is we've dropped all of the simplifying assumptions that were made by Rober and Holder in 2017. So for example, they assumed that there was infinitely many pulsars that are uniform on the sky. We instead considered the case where there's only a finite set of pulsars at specific sky locations. They assumed that there was no pulsar measurement noise, that the only thing influencing the observations was the gravitational wave background. We included sources of noise. This can be the pulsar isn't rotating smoothly, or the radio receivers introduce noise, or the arrival time of the pulse can't be precisely determined. So we allowed for an arbitrary stationary and Gaussian noise source with an arbitrary spectrum affecting these measurements. And lastly, Rober and Holder had assumed that all of the gravitational wave sources were radiating at a single fixed frequency that was commensurate with the observation time. we drop that and we just allow the gravitational wave sources to have an arbitrary power spectrum, so they can be radiating at all frequencies. And based on this, we've actually computed what the variance is, how far these Hellings and Downs correlations should come away from the Hellings and Downs expectation. And, and to illustrate that, I just wanted to show a couple of plots. So this variance, the amount by which the estimator differs from the mean, is given by a ratio. And the ratio has a numerator and a denominator. The numerator in this formula is a geometrical quantity that only depends upon where the pulsars are located on the sky. So for example, in the case of an infinite number of pulsars located uniformly on the sky, this geometrical term sigma squared g is just given by this black curve here. I've labeled it with an infinite number of pulsars. By the way, this doesn't go exactly to 0 at these points. It's near 0, but not 0. That's the best that you can do for this geometrical term. Now, in the case of nanograv that only has 67 pulsars, if I split them up into the 15 angular bins that we talked about a minute ago, you get these plus signs. So you can see the fact that they have 67 pulsars at specific sky locations rather than an infinite number, it increases the variance away from the Hellings and Downs compared to the infinite number of pulsars by perhaps a factor of 2. The denominator, and freak here, there's a nasty looking formula that I'm not going to show you. It has a nice interpretation though. It's the effective number of frequency bins in which the gravitational wave signal dominates the pulsar noise. So if the gravitational wave background is dominant in exactly one frequency bin, then this formula would have n freak equal to 1. The variance away from the Hellings and Downs correlation would just be equal to sigma squared g. And so I've plotted here in the upper curve what that would give. So here's the Hellings and Downs correlation. That's the black curve. The dotted lines here would be the variance away from that in the case of an infinite number of pulsars. And the plus symbols are the variance away from that in the case where you have the 67 nanograv pulsars. So that's nice because it gives us now a handle to understand, are pulsar timing arrays seeing the type of correlation that one would expect, or do they not agree with that? I've come to the end of my hour, and so let me just summarize where we are. So I think the detection of a gravitational wave stochastic background is not far away. We're not there yet, and it's not clear that we're going to see something of cosmological origin. It may just be radiation left behind by binary systems in the recent universe. The recent pulsar timing array is showing data that's consistent with this Hellings and Downs pattern, but we don't yet have a detection. I haven't talked too much about the possible PTA sources that might explain this background, but I think a population of supermassive black holes, binary black holes associated with galaxy mergers, that is a possible source. The data is not yet good enough to really distinguish between sources or even to say that we've seen something. I think recent work is giving clear expectations of what PTA detection would look like. I expect that coming years will see big improvements in our ability to characterize this background and hopefully 5 sigma detection. And I wanted to finish just by saying that Bernardo and Nig have published a very nice review of the field, including sort of current status and future prospects. And so if you want to learn more about that, that's a nice place to turn. Thank you.
Bruce, thank you very much for the very nice and insightful with a lot of physics in there. Thank you. Any questions from the audience? Okay, Bruce, it's Quananin online. Do you want to ask Bruce the question right away, or I can, if not, I can repeat your questions. Okay, I think I'm not, I just save time and go ahead to early on. Uh, Mr. Lin, he said, can you explain why the omega, that means the spectral density, has a decrease at no frequency for in slow roll inflation?
Okay. So let's come back to that. So you're asking about this turnover here. Is
Yes.
that right?
Yes.
Yeah, the turnover results because, so as you know, as we explained, the high frequencies come from the earlier times, and the low frequencies come from later times. So, so at the lowest frequencies here, what we're seeing is perturbations that re-entered the Hubble sphere after the universe became matter dominated. At high frequencies here, you're seeing perturbations that re-entered the Hubble sphere before that time. And what happens is that the perturbations that re-enter at later times, um, the amplitude scales differently. The equation of motion is different. I guess I can't give a simple physical argument. I should have one. It's a good question. I'll see if I can come up with a physical argument, but I don't have one in my head at the moment.
Okay.
It's a very good question, though.
Yeah. Any more questions for Bruce? Okay,
Maybe
then
I want to make one other comment about this, which is kind of curious.
go ahead. Yeah.
Since I think we have some time. So an interesting feature of this spectrum is that the number of quanta, the number of gravitons, is not conserved. And what do I mean by that? Typically, what we imagine in a background of massless radiation is that as the universe expands, each quanta, its energy redshifts like 1 over the scale factor, like 1 over A, and the number density redshifts like 1 over A cubed. So, so the energy density scales like 1 over the scale factor to the 4th. That's typical for massless radiation. And you might think that that's the case for the gravitational wave background as well. Now, that is true for the frequencies here that are above the lower limit, because for these gravitons, their energy indeed scales like 1 over the scale factor, like 1 over A. But here's an interesting fact. As the universe continues to expand, the low frequency limit here drops. And what that means, it means that new perturbations enter the Hubble sphere as quanta. And so, in fact, the number of gravitons is not fixed. As the universe continues to expand, you have more perturbations coming inside the Hubble sphere, the number of quanta goes up, and because of this steep slope, the total energy density in the gravitational radiation doesn't scale like 1 over A to the 4th. It actually scales like 1 over A cubed. The gravitons, which are already within the Hubble sphere, their energy density goes like 1 over A to the 4th, but there are new quanta being added because this low frequency limit is dropping. And actually, I described that effect in this paper in 1988. John Barrow actually wrote about this as well. He called it the Allen effect. And it's a very curious feature of inflation is that this gravitational wave background, the total energy density does not scale like 1 over A to the 4th. It scales like 1 over A cubed as the universe expands. It's a constant fraction of the matter energy density. So it's a curious feature of this steep part of the spectrum.
Yeah, thank you. Yeah, I learned a lot. Any other questions for Bruce? Okay, if no, could I ask you a question about the last slide before the conclusion about this
Sure.
cosmic variance?
Yeah. I have a very technical slide about this, but I thought I wouldn't put it up. This one here.
You mean the we can improve the cosmic variance by number of beams?
Yes. So,
Okay.
so in early work that I did on this, we defined the correlation to be a time average of the redshifts at two different pulsars.
Mhm.
And that time average, it weights uniformly all the different frequency bins. In other words, if you
True.
write that time average in frequency space, it's just an integral of z1 of f times z2 star of f df. But if we know that there's a certain spectrum of radiation, then that measure of correlation is not the optimal choice. Then you should use a filtering function or a kernel for the timing residuals, which is not uniform in time. And so what Joe and I did in this PRL is we actually worked out what the optimal way was to combine the data. And if you do that, it means that the different frequency bins get averaged not with the same weight for each frequency bin, but you can put more weight on the frequency bins where there's more gravitational wave signal and less weight on the others. So in principle, the cosmic variance could be eliminated if we could observe an infinite number of frequencies. Now, in practice, what we expect for the gravitational wave background is that it has a steep negative slope. It's falling with increasing frequency. And what that means is that there will always be some frequency above which we're dominated by pulsar noise. So right now, in the observations, this effective number of frequency bins is actually less than 1. There isn't a single frequency bin that's signal dominated. But the expectation is that as you make longer observations and gather more data, eventually there will be several frequency bins which are signal dominated. And so you can reduce the variance below this geometrical quantity. In theory, you could reduce it to 0. Effectively, what you're doing is you're averaging together different sky maps. So this paper by Ruber and Holder is very useful in that respect. And it actually reaches a similar conclusion, although it doesn't justify it very well at the end.
Yeah, nice. Yeah. Thank you.
Sure.
Okay, any other questions from the audience? Yeah, okay.
I'm having a look at the chat now, so if somebody wants to type something in the chat, I can also read it.
It seems I looked at all of them already.
Okay.
Maybe there's some chat to you only. Yeah.
No,
Okay.
no, there's no messages to me that I can see.
Yeah.
I'm just looking at the.
Okay. If
Thank you very much.
Okay, if no more questions, let's thank Professor Busela again for giving such a nice talk. Okay, thank you very much.
Okay, bye-bye.
Bye-bye.